As we all know, stellar evolution produces minerals. This is the Mohs hardness scale. This is if you can scratch the mineral, depending on the surface, will determine how hard it is. I believe talc and gypsum you can scratch with your fingernail. Calcite's a bit harder. I think you can scratch that with a penny. Fluorite is a bit harder. Apatite. Then you have orthoclase, which is basically a large component of feldspar. You can write that out. Feldspar is a very common rock. And you have quartz. I have an amethyst right here. Check it out. It's amethyst. That's quartz. And you have topaz, and basically the gemstone quality material because you can't scratch it. It's pretty resistant to being destroyed. So you have quartz, topaz, which is very beautiful. Which is just getting as much topaz as you can. And you have corundum, which is also known as ruby and sapphire. And you have diamond, which is, everybody knows diamond. It's made of carbon, C. And the chemical formulas for these, I want to go over that as well. They're all over the place. You can't really determine how hard an element or a mineral is going to be by its chemical formula. As you can see, some formulas are simpler than others, but as well some are more complex and are harder than the simple ones. So it's all over the map. But you can tell a lot by looking at the chemical formulas for these minerals. You have magnesium, which is Mg, silicon, which is Si, oxygen, which is O, and OH, the hydroxyl. You have 2 of those, you have 10 oxygens, you have 4 silicons, and you have 3 magnesiums. That's a whole lot of elements going into one molecule of talc. Okay. And you have gypsum, you have calcium, sulfur, and oxygen, 4 oxygens. In addition to that, you have 2 water molecules. So literally, gypsum is comprised of water. How about that? So basically, this formed separately than this, and then they combine later down the road to make gypsum. Pretty cool. You have calcite, which is calcium, that's fitting, carbon, and 3 oxygen. You have fluorite, which is calcium and fluorine is very, very highly electronegative. I think it's the most electronegative element, right next to oxygen. So it binds onto elements very well, as you'll see later. Apatite, calcium, 5 of those, and P is, phosphorus, and you have oxygen 4, and you have 3 of those. So literally you have 12 oxygen and 3 phosphorus atoms in there. And then this comma means it could be either a hydroxyl, which is OH, chlorine, or fluorine, which could all replace each other inside this chemical formula. So you could have it as just a hydroxyl or the chlorine or the fluorine to finish up that little spot. You have K, which is potassium, aluminum, and silicon and oxygen for orthoclase, which is feldspar, very common. Quartz is very common as well. It's a very large component of a lot of beach sand and things like that, which is silicon and 2 oxygen. Topaz, which is aluminum, silicon, and oxygen, plus the hydroxyl and the fluorine. We saw that earlier. Corundum, which is ruby and sapphire. This is aluminum and oxygen. And you have diamond, which is just carbon by itself. Now, by studying all these chemical formulas, what the actual minerals are comprised of, you can actually learn a lot about how things form in nature. Unfortunately, a lot of literature in geology, they don't ever discuss how the silicon combines with the oxygen to begin with. They just say, oh, it's the rock cycle. What they're forgetting is that the oxygen at one point had to be separate from the silicon. they were not together as well. The silicon was separate, as well as the oxygen was also separate. This oxygen was not always a molecule. The oxygen atoms were separate from each other at one point, meaning you had to have all these elements come together, okay? And what that means is in order to have these elements come together, you're probably going to have a huge amount of energy released in the form of exothermic synthesis reactions. And I'll go ahead and write that out again. Exothermic, meaning heat releasing. Synthesis, meaning combining the elements. You have oxygen combining with silicon. And reaction, meaning there was a chemical process that happened early in Earth's history which combined the oxygens first and then combined the oxygens with the silicon. That is not covered in the geological rock cycle. That's covered in stellar metamorphosis, though. These two elements formed gaseous oxygen first, which was under extreme pressures and temperatures, to where it combined with silicon in the center of gas giants. That's what gas giants are making right here. They're making topaz, they're making corundum, they're making diamonds, they're making apatite, fluorite, calcite, gypsum, talc. They're making every single chemical combination that occurs naturally inside of their interiors. Gas giants and even earlier stars, such as red dwarfs, I'm not sure that's how you spell dwarfs, maybe it's dwarves with a D. But anyways, these stars are giant chemical mixing grounds. They're giant chemical blenders. And the reason why they're releasing all the heat from or continuously, more heat than they receive from the sun. I have to erase all this. I don't want to, though. The reason why they're releasing all the heat, more heat than they receive from the sun, is because of these chemical synthesis reactions. My previous talk, remember when I talked about what an exothermic reaction is? You have the energy state is down here, and you have your activation energy, which goes up a hill, and you have the higher energy. You're low. So you have to get over that hump to get the entire system at a higher energy level. And then the endothermic reaction. Wait, do I have that backwards? Yeah, I do have that. I think this is endothermic. This is heat absorbing. But with cell evolution, it's exothermic, meaning you take the higher energy level, you give it a little bit of activation energy, and it slams back down, and it goes down here, which means the molecule will be at a lower energy state. And that's what all stars are doing. They're trying to get that activation energy to move down, to combine with each other, and make all the molecules that we see occurring naturally on Earth. And those molecules we saw inside the Mohs hardness scale of various different chemical combinations. We call those minerals. But the separate elements are up here, and the activation energy that they get to overcome that hump and to lower their energy state is in the form of gravitational potential energy. So we can possibly, in the future, do a calculation to measure the majority of the chemical combinations that we find in nature, such as rocks and minerals, and reverse engineer how much gravitational potential energy would have been required to overcome that slipped my mind. Activation energy, let me write it up here. To combine to make those synthesis reactions occur, thus releasing heat. Remember, after it overcomes that initial activation energy, it releases heat, and that's what Neptune, Uranus, Jupiter, and Saturn are doing right now. For those who aren't aware of this, the reason why I'm going over that specifically is because, okay, you have the sun. Now, it emits, let's just give an example, maybe like 10 billion watts of energy, okay? And this form is in the form of solar radiance and that kind of stuff. And you have that radiance hitting Jupiter, okay? It's a very crappy drawing of Jupiter. Now, what the scientists have realized is that the amount of energy hitting any point on Jupiter, given, you know, only shine on half of the thing because it's a ball, it's not going to shine on the entire thing. The amount of energy that the sun emits and hits Jupiter is not as much as Jupiter radiates back into the environment. Now, that's also taking into account that it's only shining on 1/2 the surface, okay, at any given point in time. Basically, even if you were to take this side of Jupiter's radiance and times it by 2, it would still radiate more energy than it receives from the sun. I think I said that right. I'm not too sure if I said that right. But anyways, what I'm saying is Jupiter emits more energy than it receives from the sun. So does Neptune. So does Uranus. So does Saturn. Okay? These objects are emitting more energy than they receive from the sun. Now, how is that even possible? These are supposed to be ice giants. Well, we've already solved that problem. The reason why they're emitting more energy from the sun is because of chemical reactions. So you have chemical reactions in the interior of these stars. They're very evolved. Chemical reactions form those rocks and minerals, and they fall inwards, forming the land and the rocks and minerals that we're familiar. And all that heat radiates back into interstellar space. So essentially it causes the star, 1, to shrink, and 2, to lose energy and to evolve. But anyways, that's why I stress rocks and minerals so much, because it's direct evidence for past chemical synthesis. Now, you won't read a lot of this in publications because simply it does not exist. Astronomers and geologists ignore chemistry.